Imagine peering into the absolute dark of the night sky, looking past the familiar stars and realizing that the blackness is actually filled with an infinite number of hidden worlds. For the longest time, humanity believed we were the absolute center of everything that existed. We looked up and saw a comforting, small ceiling of stars wrapped around our tiny world. But our true position in the grand cosmic design is far more staggering, far more humbling, and infinitely more beautiful than our ancestors ever could have dreamed. Tonight, we are going to take an incredible voyage across the breathtaking scales of space and time. We will trace how our species managed to break free from our cosmic blinders, uncovering a universe so massive that it challenges the very limits of human imagination. Let us begin our journey by stepping backward in time to an era when the universe felt small, cozy, and entirely understandable. For thousands of years, humans looked up at the night sky and assumed that what they saw was all that existed. The stars were merely bright lights fixed to a celestial sphere, and our planet sat proudly at the very heart of creation. Even as the telescope was invented and we began to map the planets, our vision remained deeply confined. We believed the entire universe was contained within just our own galaxy, the Milky Way. To the astronomers of the early 20th century, our galaxy was not just a part of the cosmos, it was the cosmos. Everything outside of this swirling collection of stars was thought to be an empty, eternal void of nothingness. However, there was a lingering mystery hiding in plain sight among the familiar stars. When astronomers looked through their early telescopes, they occasionally spotted strange blurry patches of light scattered across the night sky. They did not look like sharp points of light like normal stars, but rather resembled faint, ghostly clouds or wisps of cosmic smoke. Scientists called these mysterious objects nebulae, which is simply the Latin word for clouds. For decades, a fierce debate raged within the scientific community regarding what these blurry patches actually were. One group of scientists argued that these nebulae were merely small clouds of gas and dust drifting within our own Milky Way galaxy, perhaps representing new solar systems in the middle of forming. But another group of thinkers proposed a far more radical, almost frightening alternative. They suggested that these clouds were not inside our galaxy at all. Instead, they hypothesized that these nebulae were actually entirely separate, massive collections of stars situated at mind-boggling distances far beyond the borders of the Milky Way. They referred to them as island universes. If this second theory turned out to be correct, it would mean that the universe was vastly larger than anyone had ever imagined, and our own giant galaxy was just one minor island in a colossal, uncharted ocean of space. The debate seemed completely impossible to settle, because telescopes of that era simply lacked the power to see these clouds with enough clarity to resolve the argument. Everything changed in the early 1920s when a brilliant and determined astronomer named Edwin Hubble stepped onto the scene. Working with the newly constructed Hooker telescope on Mount Wilson in California, which was the largest and most powerful telescope in the world at that time, Hubble directed his gaze toward one specific famous blur known as the Andromeda Nebula. He spent countless cold nights exposing photographic plates, determined to peer deeper into the heart of this cosmic cloud than anyone had ever done before. His goal was to see if he could resolve individual distinct stars within the blurry, swirling mist of the nebula. After months of painstaking observation, Hubble discovered something truly extraordinary on his photographic plates. He managed to isolate individual stars within the outer arms of the Andromeda Nebula. Even more importantly, he identified a specific type of pulsing star known as a Cepheid variable. These unique stars are incredibly valuable to astronomers because they act as cosmic measuring sticks. By carefully measuring the exact speed at which a Cepheid variable pulses its light, scientists can calculate its true intrinsic brightness. By comparing that true brightness to how faint the star actually appears from Earth, they can calculate the exact distance to the star with remarkable accuracy. Hubble sat down and performed the calculations for the Cepheid variable he had discovered inside the Andromeda Nebula. The mathematical results were absolutely shocking. The star, and the entire nebula surrounding it, was not just a few hundred or a few thousand light years away. It was located millions of light years away from Earth. This distance was vastly greater than the entire estimated size of the Milky Way galaxy itself. In a single historic moment of mathematical clarity, the debate was settled forever. The Andromeda Nebula was not a small cloud of gas trapped inside our galaxy. It was an entirely independent galaxy, a massive island universe containing hundreds of billions of stars, existing completely outside of our own. With this single discovery, the boundaries of the known universe shattered wide open. The cosmos instantly expanded in the human mind by a factor of millions. Humanity woke up to a terrifying and exhilarating new reality. Our giant Milky Way galaxy was merely one of many. Hubble did not stop there. He began to observe other nebulae across the sky, finding that almost all of them were actually independent galaxies, located at incomprehensible distances. The cosmos was suddenly revealed to be a vast archipelago of stellar islands, separated by immense gulfs of dark, empty space that stretched out in every direction, farther than anyone could comprehend. As astronomers adjusted to this dizzying new perspective, they began to realize that these galaxies were not just sitting still in the void. Hubble made another monumental discovery when he analyzed the light coming from these distant stellar islands. He noticed that the light from almost every single distant galaxy was shifted toward the red end of the electromagnetic spectrum. In physics, this phenomenon is known as redshift, and it occurs when the source of light is moving rapidly away from the observer. The further away a galaxy was located from Earth, the faster it appeared to be rushing away into the deep dark. This groundbreaking observation led to the realization that the universe itself is actively expanding. It is not a static, unchanging backdrop, but a dynamic, growing fabric. Galaxies are not just flying through space. Rather, the very fabric of space between them is stretching out over time. If you could rewind this cosmic movie backward in time, you would see all these scattered galaxies drawing closer and closer together, eventually merging into a single, infinitely dense, infinitely hot point. This realization gave birth to the modern Big Bang theory, establishing that our universe had a definitive beginning, roughly 13.8 billion years ago. The fact that the universe has a specific age introduces a profound and fascinating limitation to what we can actually observe. Because light travels at a constant, finite speed, when we look out into the deep trenches of space, we are also looking backward through time. When you look at the moon, you see it as it existed a little over 1 second ago. When you look at the sun, you see it as it was 8 minutes ago. And when Edwin Hubble looked at the Andromeda Galaxy, he was seeing light that had left that galaxy 2.5 million years ago, long before modern humans walked the Earth. Consequently, there is a hard physical boundary to how much of the cosmos we can ever hope to see. This boundary is known as the observable universe. It is a sphere centered directly on us, representing the maximum distance that light could have traveled to reach our eyes since the universe first began 13.8 billion years ago. Anything that exists beyond this cosmic horizon is currently invisible to us, simply because there has not been enough time since the dawn of creation for the light from those distant regions to complete its journey across space to Earth. For decades, astronomers wondered what truly lay out there in the deepest, darkest patches of the observable universe. They wanted to know what the cosmos looked like at its absolute furthest limits. In the mid-1990s, a team of bold scientists decided to use the newly deployed Hubble Space Telescope to conduct a daring and highly controversial experiment. They decided to point this incredibly expensive, state-of-the-art space telescope at a tiny, completely empty patch of sky near the Big Dipper. To the naked eye and to ordinary ground-based telescopes, this specific patch of sky was pitch black, containing absolutely nothing but empty space. Many scientists thought this experiment was a complete waste of valuable telescope time. They argued that pointing the instrument at total darkness for days on end would yield nothing but blank images. But the directors of the project persisted. For 10 consecutive days, the Hubble Space Telescope stared unblinkingly at that single microscopic speck of dark sky, absorbing whatever faint ancient photons might be drifting through the void from the farthest reaches of time and space. The telescope collected light over a total of 342 separate exposures, slowly building an image from the darkness. When the final data was processed and the image was finally revealed to the world, it caused an absolute sensation across the global scientific community. The image, which became known as the Hubble Deep Field, was not empty at all. In that single tiny speck of sky, a patch no larger than a grain of sand held at arm's length, the telescope captured approximately 3,000 distinct objects, and with the exception of a few nearby foreground stars, every single one of those objects was an entire galaxy. There were spiral galaxies, elliptical galaxies, and chaotic colliding galaxies of all shapes, sizes, and colours, glowing like brilliant jewels in the dark. The Hubble Deep Field fundamentally altered our understanding of the cosmic population. By looking deep into a single patch of nothingness, scientists proved that the universe was packed with galaxies to a degree that defied common sense. This experiment was later repeated with even longer exposure times and more sensitive instruments, resulting in the Hubble Ultra Deep Field and the Extreme Deep Field. Each time we stared deeper into the dark, we found thousands upon thousands of additional galaxies hiding in areas where we previously thought nothing existed. By taking these deep field images and multiplying them across the entire sphere of the night sky, astronomers were able to make their first statistically sound estimates of the total number of galaxies within the observable universe. The initial numbers were staggering, suggesting there were around 100 billion galaxies out there. However, as our technology improved and we deployed even more advanced space observatories, that number was revised drastically upward. Modern calculations suggest that the observable universe actually contains at least 2 trillion individual galaxies. To truly grasp the sheer scale of that number is almost impossible for the human brain. Think about it this way. Every single one of those 2 trillion galaxies contains hundreds of billions of individual stars. If you were to multiply the number of galaxies by the average number of stars within them, you get a total number of stars that is greater than the total number of grains of sand on every beach, desert, and coastline across the entire planet Earth. And around almost every single one of those stars, there are likely planets orbiting, creating an almost infinite tapestry of worlds. As we map these trillions of galaxies, we find that they do not just drift randomly or aimlessly through the empty void of space. When we zoom out to the largest scales imaginable, a magnificent, unexpected structure begins to emerge from the darkness. Galaxies are arranged in a colossal, interconnected network known as a cosmic web. This web is the largest structural feature in the known universe, consisting of massive, glowing filaments of galaxies separated by immense, completely empty voids where virtually nothing exists. These giant filaments of galaxies are drawn together by the invisible pull of gravity, forming massive cosmic highways that stretch across hundreds of millions of light years. Where these filaments intersect, they form titanic concentrations of matter called galaxy superclusters. These superclusters are the ultimate metropolises of the cosmos, containing thousands of individual galaxies bound together in an eternal gravitational dance. Our own Milky Way is just a tiny resident on the outskirts of one of these enormous structures, known as a Laniakea supercluster. Yet, despite the unimaginable abundance of matter, stars, and galaxies tracing out this beautiful cosmic web, the most shocking revelation of modern astronomy is that all of this visible matter is just a tiny fraction of what actually exists. Everything we can see with our eyes, everything we can detect with our most advanced radio telescopes, and everything that shines in the night sky accounts for a mere 5% of the total mass and energy of the universe. The remaining 95% of the cosmos is completely invisible, made up of mysterious components known as dark matter and dark energy. Dark matter acts as an invisible cosmic scaffolding, providing the extra gravitational pull needed to hold fast-spinning galaxies and massive superclusters together. Without it, galaxies would fly apart into chaos. Dark energy, on the other hand, is an enigmatic force that permeates all of space, driving the accelerating expansion of the universe and pushing galaxies farther apart at an ever-increasing velocity. We are living in a universe dominated by mysteries that we can barely detect, floating on a tiny raft of normal matter in a vast ocean of darkness. This realization brings us to a profound and bittersweet understanding of our place in time. Because dark energy is causing the expansion of the universe to speed up, the distant galaxies we see today are accelerating away from us at faster and faster speeds. Eventually, billions of years from now, they will be moving away so quickly that their light will no longer be able to bridge the widening gap to reach Earth. The beautiful cosmic web will stretch so far that our neighbouring galaxies will vanish from our sight completely. Future generations of astronomers living trillions of years from now will look up at a completely dark, empty night sky, unable to see a single galaxy beyond their own. They will have no way of knowing that a vast universe of 2 trillion galaxies ever existed. We happen to occupy a uniquely privileged window in cosmic history, a sweet spot in time where the universe is old enough to have formed intelligent life capable of building telescopes, yet young enough that the grand, glittering architecture of the cosmos remains fully visible to anyone who dares to look up into the dark. To understand how we can even attempt to survey this massive expanse, we have to look closely at the light that travels through it. Light is the ultimate cosmic messenger. It carries the secrets of distant stars across billions of trillions of miles, crossing the empty voids of space to reach our tiny world. For a very long time, humanity could only perceive the universe through the narrow window of visible light. This is the tiny band of colours that our human eyes evolved to see, stretching from deep violet to dark red. We mistakenly assumed that this small rainbow represented the entirety of reality. We thought that if a patch of space looked completely dark to our eyes, it meant there was absolutely nothing there to see. But this perspective was incredibly limited. Visible light is actually just a tiny microscopic sliver of a much larger reality known as the electromagnetic spectrum. Surrounding the familiar colours we can see is a vast hidden universe of invisible energies. There are radio waves that stretch as long as houses, infrared rays that carry heat through the darkness, ultraviolet rays that burn our skin, and high-energy X-rays and gamma rays that are born in the violent deaths of giant stars. When astronomers realized that the universe was singing in all of these invisible frequencies, they knew they had to build new kinds of eyes. They needed telescopes that could see the unseen, revealing a cosmos that had remained completely hidden from human sight since the beginning of time. One of the most revolutionary breakthroughs came when scientists developed the ability to see in the infrared spectrum. Infrared light is essentially heat radiation. It is completely invisible to human eyes, but it possesses a magical property that visible light lacks. It can pass right through thick, dense clouds of cosmic dust. In our galaxy and in every other galaxy across the universe, there are gigantic dark clouds of interstellar gas and soot. These clouds act like thick, heavy curtains, completely blocking our view of what lies behind them. When we look at these regions with normal optical telescopes, they appear as completely black, empty holes in the fabric of space, empty voids where no stars seem to exist. However, when we turn an infrared telescope toward those exact same black spaces, the heavy cosmic curtains suddenly become completely transparent. The infrared light emitted by objects hidden deep inside the dust can pass through the particles without being scattered or blocked. Suddenly, the darkness is revealed to be a nursery of frantic activity. We can see thousands of newborn stars blinking into existence inside the dust, surrounded by swirling disks of rock and gas that will eventually form entirely new planetary systems. Seeing in infrared allows us to lift the veil of the universe, letting us look directly into the hidden rooms where cosmic creation takes place. This ability to pierce the dust became the driving force behind one of humanity's greatest scientific achievements, the construction and deployment of the James Webb Space Telescope. For decades, engineers and scientists worked to create a machine that could see the infrared universe with unprecedented clarity. The telescope needed a massive gold-coated mirror to collect the incredibly faint infrared light traveling from the edge of time. Because infrared light is heat, the entire telescope had to be kept at temperatures close to absolute zero so that its own warmth would not blind its sensitive instruments. It had to be launched 1 million miles away from Earth, protected by a giant sunshield the size of a tennis court. When the James Webb Space Telescope finally opened its golden eye and beamed its first images back to Earth, the results left the world completely breathless. The pictures were sharper, deeper, and more detailed than anything we had ever seen before. We could see the intricate, jagged edges of cosmic cliffs in stellar nurseries, and we could detect the faint, ancient glow of the very first galaxies that formed after the Big Bang. These galaxies were so far away that their light had been travelling for over 13 billion years to reach us. Because the universe has been expanding during that entire time, the light waves have been stretched out, transforming from visible light into invisible infrared wavelengths. Without infrared eyes, these ancient cosmic pioneers would remain lost to us forever. As we use these advanced tools to look closer at individual galaxies, we find that they are not just static collections of stars, but complex, changing ecosystems. Within a single galaxy like our own Milky Way, there is a continuous, beautiful cycle of life, death, and rebirth. It begins inside the giant molecular clouds, the vast nebula complexes made of hydrogen gas and cosmic dust. Under the relentless, steady pull of gravity, these clouds begin to collapse inward on themselves. As the gas squeezes tighter and tighter together, the temperature and pressure at the center begin to skyrocket. Eventually, the pressure becomes so intense that it forces individual atoms of hydrogen to smash together and fuse into helium. This process is called nuclear fusion, and it releases an absolutely immense amount of energy. In that exact instant, a star is born. The outward pressure generated by this nuclear fire balances against the inward pull of gravity, creating a stable, glowing ball of plasma that can shine steadily for millions or even billions of years. This is the long, stable adult life of a star, the period during which it warms the surrounding space and provides light to whatever planets might be orbiting around it. But no star can burn forever. Eventually, the hydrogen fuel at the core begins to run out, and the delicate balance between gravity and nuclear pressure is broken. What happens next depends entirely on the mass of the star. Small stars, like our Sun, experience a relatively slow and gentle ending. As their core runs out of fuel, they swell up into giant red spheres, swallowing up their innermost planets. Eventually, they gently puff their outer layers of gas into space, creating beautiful glowing shrouds known as planetary nebulae. The glowing core that remains behind is a tiny, dense remnant called a white dwarf, which slowly cools down over trillions of years until it goes dark. For massive stars, stars that are many times larger than our Sun, the end is far more dramatic and violent. When these giants run out of fuel, their core collapses in a matter of seconds, triggering a colossal explosion known as a supernova. This explosion is so incredibly powerful that it can briefly outshine an entire galaxy of hundreds of billions of stars. The shockwave rips through space, tearing the star apart and scattering its elements across the cosmos. What remains at the absolute center of the blast is compressed into an object of terrifying density, either a rapidly spinning neutron star or a bottomless pit in the fabric of space-time known as a black hole. This violent cycle of stellar death is not just a destructive event, it is the ultimate source of everything we see around us. The Big Bang only created the simplest elements in the universe: hydrogen, helium, and a tiny bit of lithium. If the universe had stopped there, no planets could ever have formed, and life would be completely impossible. The heavier elements that make up our world, the iron in our blood, the calcium in our bones, the oxygen we breathe, and the silicon inside our technology, did not exist at the beginning of time. They had to be forged inside the white-hot nuclear furnaces of giant stars. When these massive stars die in spectacular supernova explosions, they blast these newly created heavy elements out into the interstellar void. The scattered iron, carbon, and oxygen mix with the existing clouds of hydrogen gas, enriching them with the raw ingredients needed to build more complex things. Over millions of years, these enriched clouds collapse to form new generations of stars and planets. Our own solar system is the product of this cosmic recycling program. We, and everything on our planet, are literally made of recycled star stuff, forged in the hearts of dying suns billions of years ago. When we look at the planets that form around these newer generations of stars, we are finding that the universe is far more creative than we ever suspected. For centuries, the only planets we knew about were the ones inside our own solar system. We assumed that other star systems would look just like ours, with small rocky planets close to the star and large gas giants sitting farther out in the cold. But in the mid-1990s, astronomers developed techniques to detect planets orbiting distant stars, worlds known as exoplanets. This opened up a whole new field of discovery that turned our assumptions completely upside down. One of the most surprising early discoveries was a class of worlds called hot Jupiters. These are massive gas giant planets, similar in size to Jupiter, or even larger, that orbit incredibly close to their parent stars. They are so close that their years last only a few days, and their atmospheres are heated to thousands of degrees, causing them to glow with a dull heat. According to our traditional theories of how solar systems form, it should be completely impossible for a giant gas planet to exist so close to the burning heat of a star. Their existence forced scientists to completely rewrite their models, realizing that planets can migrate across vast distances over time, shifting their orbits in a chaotic cosmic dance. To find these hidden worlds, astronomers had to develop incredibly clever methods, because planets do not emit their own light and are completely lost in the overwhelming glare of their parent suns. One of the most successful techniques is known as the transit method. This involves watching a distant star very carefully over long periods of time, measuring its brightness with extreme precision. If a planet happens to pass directly between that star and our telescopes on Earth, it will block a tiny, minuscule fraction of the star's light. The star will appear to dim slightly for a few hours, before returning to its normal brightness. By analysing the exact shape and depth of this dip in light, astronomers can determine how large the planet is and how fast it is orbiting its star. If the dip happens regularly, say every 30 days, we know the planet takes 30 days to complete 1 year. Space telescopes like Kepler and TESS spent years staring at hundreds of thousands of stars simultaneously, watching for these tiny rhythmic dips in brightness. Through their tireless work, they discovered thousands of confirmed exoplanets, proving that planets are not rare anomalies, but are a completely standard feature of the cosmic landscape. Another brilliant method used to find these worlds is the radial velocity method, often called the wobble method. Just as a star's gravity pulls on a planet to keep it in orbit, the planet's gravity also pulls back on the star. Because the star is so much heavier, it does not move very much, but it does execute a tiny circular wobble in place as the planet circles around it. As the star wobbles toward Earth, its light is compressed slightly, shifting toward the blue end of the spectrum. As it wobbles away, its light stretches out, shifting toward the red. By measuring these tiny periodic shifts in colour, scientists can calculate the mass of the hidden planet causing the wobble. As our planetary catalogue grew from dozens to thousands, we began to discover worlds that look completely alien compared to anything we have in our own neighbourhood. We found super-Earths, which are rocky worlds that are significantly larger and heavier than our planet, but smaller than ice giants like Neptune. We found ocean worlds completely covered by water hundreds of miles deep, with no solid land anywhere in sight. We even found planets orbiting binary star systems, worlds that have two suns in their sky, where a sunset looks like something straight out of a science fiction movie. Among all of these discoveries, the ultimate prize for astronomers is finding an Earth-sized planet sitting in what is known as the habitable zone, or the Goldilocks zone. This is the specific region around a star where the temperature is just right, not too hot and not too cold. If a planet is too close to its star, any liquid water on its surface will boil away into steam. If it is too far away, the water will freeze solid into ice. But inside the Goldilocks zone, a planet can maintain liquid water on its surface, which is the foundational ingredient needed for life as we know it to exist. Finding a planet in this zone is just the first step. To truly understand if a world could support life, we need to analyze its atmosphere. When a planet transits in front of its star, some of the starlight passes directly through the thin layer of gas surrounding the planet before traveling to Earth. Different chemical elements and molecules absorb very specific wavelengths of light, leaving unique dark lines in the spectrum like a chemical fingerprint. By carefully analyzing this filtered starlight, scientists can determine exactly what gases make up the planet's atmosphere, searching for signs of water vapor, carbon dioxide, oxygen, or methane. The hunt for these atmospheric signatures has become one of the primary missions of our newest observatories. We are no longer just asking if other planets exist. We are actively trying to see if they have weather, if they have clouds, and if they possess the chemical imbalances that would signal the presence of a living biosphere. Every time we look at a new star system, the data reminds us that our own Earth is not an isolated miracle, but part of a vast, diverse family of worlds scattered throughout the stellar neighborhoods of our galaxy. The scale of this planetary abundance is truly mind-boggling. Based on the statistics gathered by our planet-hunting telescopes, scientists estimate that there is, on average, at least one planet for every single star in the Milky Way galaxy. This means there are at least 100 billion to 400 billion planets in our galaxy alone, and when you restrict that number to just rocky planets sitting inside the habitable zones of stars similar to our Sun, the numbers still reach into the billions. The cosmos is practically teeming with real estate, offering an incomprehensible number of stages where the story of life could potentially unfold. The historic realization that those thousands of mysterious spiral nebulae were actually separate, independent galaxies, each a massive island universe stretching across immense distances, completely transformed our baseline perspective of creation. It is difficult to fully appreciate just how profound a psychological shock this was for the global scientific community and for humanity as a whole. In the brief span of only a few years, our species was forced to accept that we were not living in a cozy, singular cosmic structure that comprised all of existence. Instead, we learned that we were inhabiting a tiny, quiet corner of a boundless cosmos, completely filled with galaxies, extending outward in every direction, just as far as our most powerful telescopes could manage to see. With this monumental paradigm shift established, the obvious next question immediately surfaced, a question that defines the core of everything we are exploring tonight. If there are indeed other entirely separate galaxies out there scattered across the dark, then exactly how many of them are there? Are we talking about hundreds of them, thousands of them, millions of them, or a number that climbs so far beyond human comprehension that our language lacks the words to describe it? Edwin Hubble was far from finished with his historic work of rewriting our collective picture of the cosmos. Having decisively proven that the faint spiral structures were actually immensely distant galaxies, he and several other pioneering astronomers immediately began measuring not just the specific distances to these objects, but also the precise ways they were moving through the void. What they uncovered next was truly astonishing to everyone. They observed that almost every single galaxy they could find was actively rushing away from us. This was not a phenomenon restricted to just a few isolated clusters. Nearly all of them, in every single direction we could point a telescope, were fleeing into the deep dark. Even more remarkable was the fact that the further away a particular galaxy was located from Earth, the faster it appeared to be moving away. This direct relationship that more distant galaxies recede from us with greater velocity became one of the foundational bedrock discoveries of modern scientific history. It permanently revealed to us that the universe is not a static, eternal, and unchanging backdrop, but is actively expanding. It is vital to understand that these galaxies are not simply flying apart through pre-existing space like scattered fragments thrown out by a conventional explosion. Rather, the very fabric of space itself is stretching and expanding over time, and the galaxies are merely being carried along with it, like raisins embedded in a loaf of bread that slowly swells up as it bakes. Every single raisin drifts steadily away from every other raisin, because the underlying dough between them is growing. This singular, breathtaking insight that the universe is actively expanding would later lead scientists to a logical conclusion when they mentally ran the cosmic movie backward in time. If space is expanding today, it means that yesterday it was smaller, and billions of years ago it must have been compressed together. This realization gave rise to the concept that everything in existence originally began from an unimaginably hot, dense state, roughly 13.8 billion years ago. For our primary investigation tonight, this monumental discovery of cosmic expansion matters for another highly practical reason. The specific way a distant galaxy's light is stretched out by the expanding fabric of the universe causes that light to shift toward longer, redder wavelengths. This phenomenon became an invaluable tool for astronomers, who realized that by measuring exactly how much a galaxy's light has been stretched, they could accurately estimate how far away it lies in space and precisely how far back in time we are seeing it. This method forms a vital part of what astronomers refer to as the cosmic distance ladder. The distance ladder is essentially a series of overlapping observational techniques, where each individual rung reaches further into the deep dark than the last one could manage. The very first rungs of this metaphorical ladder are nearby and highly direct. We can measure the distances to relatively close stars by carefully watching how their positions shift slightly against the distant background stars as Earth moves in its orbit around the Sun. The next rung up the ladder relies on those uniquely pulsing Cepheid variable stars, the exact same kind of cosmic measuring sticks that Hubble used in his study of the Andromeda galaxy, to reach across the empty gulfs to our neighbouring galaxies. Further out into the deep trenches of space, where even individual Cepheid stars finally fade from our view, astronomers must rely on a special kind of stellar explosion. This is a particular type of supernova that always detonates with almost the exact same intrinsic, true brightness. Because these specific supernovae always explode with a known absolute power, they serve as brilliant cosmic beacons visible across billions of light years of space. By comparing how bright these explosions truly are to how faint they actually appear to our detectors on Earth, we can measure truly staggering distances across the void. Beyond even the reach of these supernovae, we lean heavily on the redshift itself, the direct stretching of the light waves by the expanding universe, to gauge the distances to the most remote galaxies in the known cosmos. Rung by rung, this magnificent ladder allows humanity to climb out from our own immediate stellar backyard to the very edge of the visible universe. Without this structural tool, the core question of how many galaxies exist could never even be approached, because to count galaxies accurately, you must first know how far away they are, how much total space they fill, and how far back into the history of time you are looking. For several decades following Hubble's historic breakthrough, astronomers had no definitive way to resolve that population count. They could easily count the galaxies that were visible through their ground-based telescopes, but their instruments could only peer so far into the darkness. The galaxies they were able to observe were merely the brightest, closest ones in our immediate cosmic neighbourhood. Beyond those visible markers lay an absolute ocean of darkness, and nobody knew how full or how empty that darkness truly was. The ultimate breakthrough finally arrived in the 1990s, with the deployment of a telescope that had been lifted entirely above the blurry, distorting atmosphere of the Earth, the Hubble Space Telescope, named in direct honour of the very man who had first proven that other galaxies existed. This major breakthrough came as the direct result of one of the boldest, most controversial, and strangest decisions in the entire history of modern astronomy. The director of the Space Telescope decided to commit a significant amount of operational time to an experiment that, on the surface, sounded completely wasteful to many scientists, he decided to point this incredibly expensive, highly in-demand space telescope at a patch of the night sky that appeared to be completely, utterly empty. This target was a small, dark, and utterly unremarkable speck, located near the handle of the Big Dipper, a region where there were no known bright stars, no known galaxies, and absolutely nothing of interest to conventional astronomy. To the human eye, it looked like pure black nothingness. The specific patch of sky selected was incredibly tiny. If you were to hold a single grain of sand at arm's length up against the night sky, that tiny grain would cover roughly the exact same amount of space as the telescope's target. The operational plan was to have the telescope stare unblinkingly at that single microscopic dark grain of the sky for 10 straight days, slowly soaking up whatever faint individual particles of light might happen to drift in from that direction across the vastness of space. Many prominent scientists believed this gamble bordered on absolute madness, openly questioning what would happen if there was nothing there to see. They worried that 10 days of one of humanity's most valuable scientific instruments would be utterly wasted on a blank picture of empty blackness. Yet, despite the intense criticism, the telescope opened its mechanical eye on that dark little patch of sky and held its gaze steady for days on end, quietly gathering the faintest, most ancient whispers of light. When the data collection was complete and the final image was processed, the results shocked the world. That tiny patch of supposedly empty sky was not empty at all. It was crowded, teeming, and absolutely alive with structure. In that single grain of darkness, the telescope captured thousands of distinct objects, and with the exception of a few nearby foreground stars, every single one of those objects was an entire independent galaxy, glowing brilliantly against the dark canvas of the deep universe, while the great advanced telescopes peer incredibly deep at individual highly specific patches of sky. An entirely different kind of scientific effort has been quietly and profoundly transforming our baseline picture of the cosmos. Instead of dedicating weeks to staring very deeply at one tiny, isolated spot on the cosmic canvas, a group of determined astronomers have launched vast, sweeping surveys that intentionally map huge swaths of the visible sky. Their goal is to systematically chart the precise positions and physical distances of millions upon millions of individual galaxies scattered across space. One of the first great pioneering efforts of this kind spent several years systematically photographing the overhead sky and measuring the exact distances to over 1 million distinct galaxies. By doing so, they constructed the first truly large, comprehensive, three-dimensional map of our immediate cosmic surroundings. This historic map revealed for the very first time, in exquisite and complete detail, the existence of the great cosmic web. It showed that galaxies are not just scattered randomly like spilled salt through the void, but are instead woven into massive glowing filaments and dense clusters that are separated by vast, completely empty spaces, known as cosmic voids. These colossal structures form the foundational architecture of the universe when viewed on the absolute largest imaginable scales. More recent cosmic mapping surveys have grown significantly more ambitious still, pushing the boundaries of our technology. One major international project, designed specifically to probe the deepest nature of the universe's ongoing expansion, has been meticulously measuring the distances to tens of millions of individual galaxies. To accomplish this staggering feat, the project utilizes thousands of tiny, highly sophisticated, robotic optical fibers that automatically align themselves to capture the incoming light of thousands of separate galaxies simultaneously. This technological marvel is allowing scientists to rapidly build the single largest three-dimensional map of the cosmos ever made in human history. At the exact same time, a dedicated space telescope has begun surveying enormous, unprecedented regions of the sky from its vantage point beyond the blurry atmosphere of Earth. It operates with the explicit, focused goal of charting the exact shapes, volumes, and positions of well over 1 billion distinct galaxies. By collecting this mountain of structural data, scientists hope to study the mysterious, invisible influence of dark energy, which is actively driving the universe apart at an accelerating rate. These grand, sweeping surveys do not always see the faintest, most deeply buried, or most distant galaxies that the highly focused deep field images manage to capture. However, they accomplish something that is just as important for our understanding. They completely reveal the structural architecture of the universe. They illuminate the grand, interconnected pattern into which all of those individual galaxies are beautifully woven. Furthermore, they provide the crucial baseline statistics that scientists absolutely require to accurately estimate how galaxies are distributed across the vast, empty expanses of all space. Every single one of these structural maps, with its millions of glittering individual points of data, represents humanity slowly and carefully filling in the grand census of the cosmos, one section of the sky at a time. And every single one of these completed maps invariably confirms the exact same humbling truth. No matter where we choose to point our instruments, and in every single direction we look, the universe is utterly filled with galaxies. They are scattered across the dark void in numbers that climb so incredibly high that they completely escape human comprehension. Let us pause our journey for a moment to truly consider what all of this means when you take these findings and multiply them out across the cosmos. First, hold tightly in your mind the sheer, staggering physical scale of just one single galaxy. Our home galaxy, the Milky Way, is so unbelievably large that a particle of light, moving at the absolute cosmic speed limit of 186,000 miles every single second, takes around 100,000 years simply to travel from one outer edge to the exact opposite side. Within that incomprehensible, vast structural span live somewhere between 100 billion and 400 billion individual stars, and around a great many of those billions of stars orbit an even greater number of planets. Every single star you have ever looked at in your life, every historical story that humans have ever told about the night sky, and every constellation we have ever mapped fits completely inside this single galaxy. And this one lone galaxy, which is already vast, completely beyond all human experience and imagination, is just one single, solitary point among the countless points we are actively trying to count across the universe. Now, let us begin the multiplication. Let us take even the most conservative, careful estimate provided by modern science, which places the number of galaxies at a couple hundred billion. Now consider that an average standard galaxy contains very roughly around 100 million to a few hundred billion stars, keeping in mind that the vast majority of galaxies are actually small, dim dwarfs sitting on the lower end of that population range. When you multiply the estimated number of galaxies in existence by the average number of stars contained within each one, you arrive at a total figure for the number of stars in the observable universe. And that resulting figure is a number so large that it is almost entirely beyond the capacity of human language to express. The total number of stars in the observable universe is estimated to be somewhere in the unbelievable range of a number written simply as a 1 followed by 22 zeros, or perhaps even a 1 followed by 24 zeros. There is a brilliant classic comparison that astronomers absolutely love to make to help people visualize this number, and for once, the comparison is completely accurate. If you were to travel to every single ocean beach on the face of the earth, and you were to walk along every coastline of every continent and every island, from the massive sandy expanses of the Sahara to the tiniest tropical shores, and you were to somehow count every single individual grain of sand on the entire planet, you would still not reach that number. The total number of stars burning in the observable universe is significantly greater than the total number of grains of sand on all of planet Earth, and each one of those stars could potentially host its own family of planets, moons, and worlds. Yet, even as we struggle to comprehend these numbers, a profound and complicating factor emerges that changes the entire nature of our census, the concept of the observable universe itself. When we state that there are hundreds of billions of galaxies, we are not talking about the entire universe. We are talking specifically about a tight, spherical bubble of space centered directly on us. This is the region of the cosmos from which light has had enough time to travel across the void to reach our eyes since the universe first began 13.8 billion years ago. The radius of this observable bubble is not 13.8 billion light years, as one might logically assume, because the universe has been actively expanding while that light has been traveling. Instead, the observable universe stretches out to a distance of roughly 46.5 billion light years in every single direction, creating a grand bubble that spans nearly 93 billion light years across. But what lies beyond the boundary of this massive bubble? The laws of physics and our current cosmological models tell us that there is absolutely no reason to believe the universe simply stops at the edge of our vision. There is no physical wall, no sudden drop-off into empty nothingness, and no boundary marker. If you were to magically teleport to a galaxy sitting right at the absolute edge of our observable bubble, you would look out and see a night sky that looks virtually identical to ours. You would find yourself at the center of your own new observable bubble, stretching out 46.5 billion light years in every direction, filled with the exact same cosmic web of filaments, clusters, and billions of galaxies. This means that the true, absolute universe is almost certainly far larger than the tiny sliver we are permitted to observe. In fact, our leading scientific theories regarding the earliest fractions of a second after the Big Bang, a period known as cosmic inflation, suggest that the universe underwent a burst of hyper-expansion so violent and rapid that it stretched space far beyond what light could ever hope to cross. According to these mathematical models, the total unobservable universe could easily be millions, billions, or even trillions of times larger than the observable bubble we can see. It is even highly possible that the universe is completely, utterly infinite in extent, stretching out forever without any end. If the universe is truly infinite, then the answer to our original question becomes both simple and completely terrifying. If space goes on forever, and the distribution of matter remains relatively uniform on the largest scales, then the total number of galaxies in existence cannot be written down as a finite number. The true number of galaxies would be infinite. There would be an infinite number of bright spirals, an infinite number of dwarf galaxies, and an infinite number of stars. This boundary between what we can see and what is forever hidden from us is a fundamental law of nature, dictated by the speed of light and the age of the cosmos. To better understand this cosmic limitation, we must look closer at the force that governs the large-scale behavior of the universe. For most of the 20th century, astronomers worked under the firm assumption that while the universe was expanding, that expansion had to be slowing down over time. They reasoned that the mutual gravitational pull of all the hundreds of billions of galaxies, all the stars, and all the gas in the cosmos would act like a continuous brake, gently pulling back on the fabric of space and slowing its outward growth. It was a perfectly logical conclusion based on everything we knew about gravity. But in the late 1990s, two independent teams of competing astronomers set out to measure this expected slowing down by observing incredibly distant exploding stars known as type Ia supernovae. When they finalized their data and analyzed the brightness of these distant beacons, they discovered something that completely shocked the scientific world. The expansion of the universe was not slowing down at all. It was actively speeding up. Something completely unknown was actively pushing the fabric of space apart, completely overwhelming the inward gravitational pull of all the matter in the cosmos, and accelerating the growth of the universe at an ever-increasing rate. Today, scientists call this mysterious repelling force dark energy. We do not know what dark energy actually is, what it is made of, or how it operates on a fundamental level. It remains one of the greatest, most profound mysteries in all of modern science. We only know that it is real, that it is completely uniform across space, and that it appears to make up roughly 68% of the total energy and matter content of the entire universe. It vastly outweighs all the normal matter, all the stars, planets, gas clouds, and living things combined, which makes up a meager 5% of the cosmos. The rest is dark matter, another invisible substance that acts like a gravitational glue holding galaxies together. This means that dark energy is steadily winning the grand cosmic tug of war against gravity. It is stretching the fabric of space faster and faster with every passing second, carrying distant galaxies away from us at continuously increasing velocities. This accelerating expansion creates a dramatic and bittersweet reality for the future of astronomy. Because space is stretching between the galaxies, the distance between our local group of galaxies and the rest of the universe is growing rapidly. Eventually, the expansion will become so fast that the light leaving distant galaxies will no longer be able to cross the expanding gulf of space to reach our telescopes. Over billions of years to come, galaxies that we can see clearly today will slowly fade from view, their light stretched out into infinitely long, undetectable wavelengths by the relentless growth of space. One by one, the distant island universes will slip across our cosmic horizon, disappearing into the unobservable dark forever. In the ultra-distant future, trillions of years from now, any intelligent beings living inside our galaxy will look up at the night sky and see absolutely nothing but the stars of our own merged local system. The rest of the universe will have raced beyond the horizon of visibility. All the hundreds of billions of galaxies we have worked so hard to map and count will be completely gone from sight, leaving no trace that they ever existed. This realization underscores how incredibly privileged we are to live in this specific era of cosmic history. We live at a time when the universe is still young enough and close enough for its deepest secrets to be read. We have the technology to build golden eyes that can pierce the dust, space telescopes that can stare into the blank dark, and automated fiber optic arrays that can map the architecture of the cosmic web. We are actively participating in the grandest census ever attempted, slowly piecing together the true scale of creation while the cosmic window remains wide open for us to look through. To truly understand what happens at these absolute boundaries of our view, we have to look closely at what happened at the very beginning of cosmic time. When we calculate the vast populations of galaxies that fill our observable bubble, we are not looking at a static snapshot of space. We are looking at a living, breathing history book that spans 13.8 billion years of cosmic evolution. As we trace this incredible history backward, we find that the massive, majestic galaxies we see today did not always exist in their current forms. In the earliest epochs of the cosmos, right after the first generation of stars lit up the darkness, the universe looked entirely different. Galaxies were much smaller, closer together, and far more chaotic than the beautiful grand design spirals we inhabit today. These ancient proto-galaxies were essentially small, messy clumps of pristine hydrogen and helium gas, crashing into one another in a frantic gravity-driven dance. Because the universe was significantly smaller back then, these collisions happened constantly, with smaller systems merging together over billions of years to build up the titanic stellar cities that define our modern sky. Every time two of these early systems collided, the immense shock waves would trigger a massive, furious wave of new star formation, illuminating the young universe with a brilliant, intense light. When our deepest space observatories peer into the dark, they are catching these small, irregular ancestral systems in the very act of growing, allowing us to witness the fundamental construction phases of the cosmos itself. This historical perspective completely alters how we approach our census of the universe. When we ask how many galaxies exist, the answer actually changes depending on which point in cosmic history you are asking about. If we could somehow see every single faint, tiny clump that existed in the distant past, the sheer number of individual structures would be staggering. Many of those early clumps no longer exist as independent objects today because they have long since been swallowed up or merged into larger modern galaxies like our own Milky Way. Therefore, the counting process is inherently intertwined with the passage of time itself, requiring us to map not just where things are in three-dimensional space, but also when they existed in the grand timeline of creation. As we bring our journey toward its final destination, we are left with a profound sense of awe regarding humanity's place in this immense tapestry. We started, as a primitive species, looking up at a small, comforting ceiling of nearby stars, completely unaware of the vast depths that lay hidden beyond our sight. Through centuries of patient observation, clever mathematics, and sheer technological will, we managed to shatter those early boundaries. We discovered that our sun is just one of billions in a sprawling stellar island, and that our island is merely one out of trillions of others tracing out a magnificent, glowing cosmic web across a boundless expanse of space. The fact that we can even stand on our tiny, fragile, rocky world and confidently measure the distances to these remote galactic structures is a testament to the power of human curiosity. We have built eyes that can see the invisible heat of newborn stars, mapped the grand architecture of the universe on its largest scales, and decoded the faint, ancient photons that have been travelling across the void since the dawn of time. We have confronted a reality so colossally massive that it threatens to make our entire existence feel completely small and insignificant by comparison. Yet the very act of our understanding elevates us, linking our small minds to the grand design of the cosmos. It may be that there are exactly 2 trillion galaxies contained within our visible horizon, or it may be that in the true fullness of all that exists, the universe stretches out forever without any boundary or end. But the simple act of looking up into the dark and asking these deep questions belongs entirely to us. In an expanding universe, this staggeringly vast, silent, and empty, the beautiful fact that anyone is here to ask the question at all may very well be the rarest, most precious, and most extraordinary miracle of all. Thank you for spending this valuable time with me tonight, journeying far out past the edge of our own galaxy, across the luminous threads of the cosmic web, and directly to the absolute limits of what can be counted. If this deep exploration gave you a completely new sense of wonder, please consider liking this video and subscribing to the channel. It genuinely helps more than you could ever know, and it allows us to keep reaching out into the great dark to share these incredible stories of creation